Welcome to the next lecture of switching theory and logic design. In this class, we are going to discuss the concept of counters. Right. Here, the counter is a sequential circuit. Generally, in the digital electronics, for the computation processes or different types of applications, we are using the counters concept, where a counter is a device which is used to count a number of clock signals, or by using the clock signals we can count number of events which is regularly occurred. Right? Simply the counter which stores a lot of counting operations for doing some of the events. Let us see the definition of counter once again. A counter is a circuit that produces a numerical value or count each time an input clock pulse makes an active transition. So whenever the input clock pulse is activated, then the counter, it stores a new count value. For example, the counter initially it is represented with 0. So when you are given the first clock pulse, the counter output is representing as 0, 0, 0, 1. So when you have given the second clock pulse, then the counter will represent 0, 0, 1, 0, where this value is equal to decimal 2. So like that, so the counting will be continuous when you are giving the clock pulses based on your designed circuit. For example, if you designed a 4-bit counter, so the counting starts from 0 to 0. For the first clock pulse it will show 1, second clock pulse the answer is 2, for the third clock pulse the answer is 3, for the fourth clock pulse the answer is 5. Like that it is incrementing. So one by one it is incrementing and it stores the value. Okay, so this is the behavior of the counter. So see here, for example, if you take an example, here I have taken the 4-bit counter. Here I am giving the input as a clock signal and I am taking the binary output combinations. Here I have 4 binary output combinations. So for that reason, this type of counter I can call as 4-bit counter. This counter I can call as a 4-bit counter. Maybe I have 4 outputs or 10 outputs or 20 outputs. That is based on our requirement. Here I have used 4-bit counter. Right. Let us come to the next issue. So where this counter is used, generally what are the applications of the counter? So see the applications of the counter. First, system clock. So system clock means presently we have a lot of mobiles and laptops, electronic components. So almost all in our house. So even the sweeping machine is also available in our regular houses. So for all these machines, they are working with some internal system clock. So for designing the system clock, we need the counter. For example, we have automatic room cleaning machine. This automatic room cleaning machine, almost all it will takes 2 times per day for the cleaning the house. When it is going to clean the floor, it will take some particular time. Morning 7 o'clock, the machine is going to be activated when we have programmed for the 7 o'clock. So at that time, the machine is going to start and it will roam the complete house and it will clean all the floor and the dust. Okay, which is the dust available on the floor, it will be cleared by using that machine. So in the same way, we can write the program for the night 7 AM also. Daily you can write that program for that machine 2 times. So like that, if you want 3 times, you can write the program for the 3 times. Otherwise 5 times, 10 times. In generally shopping complexes, so much of dust is there on the floors. So for that, you have to write a program for every 2 hours. The machine has to go automatically and clean the floor. So that is the program you are giving. So here it will check. So what is the time now? So now the time is 7. So they programmed for every 2 hours. So if I want to start the program again, I have to pass 120 minutes. So after each minute, otherwise after each second, it will count the time. So after completion of 120 minutes, it will starts going for cleaning. Okay, like that the system clocks are available. Next, timer and delays. So generally for representing the timers and delays. For example, in the running race, when you are doing the running, so at that particular time, they will count our time. So for example, 100 meters race, you have to complete within 11 seconds. Then they will put a timer. Otherwise, for each participant of the running race, they will put some time. So based on that information, you can analyze that how much time you have taken to complete a 100 meters round or 20 meters race or 500 meters race. Like that, you can use the timers and delays also. Next, these counters you can use watches, clocks, alarms, and counting events. Next, memory addressing and frequency divisions and sequence control and cyclic control. So we have a lot of application. When we have the currency counting machine. So for example, if you place some notes, the machine counts and it will says how many notes are available. So coin vending machine is there. So we have a lot of machineries which are using this counting operations. So these are the almost a lot of applications are available in our daily life. Now coming to here, how many types of counters are available in generally market? Here we have totally 2 types of counters are available. Totally 2 types of counters. They are, first one is a synchronous counter and second one is asynchronous counter. So synchronous counters, asynchronous counters. Where synchronous counter is consisting of a group of flip-flops. All the flip-flops are connected to a single clock pulse. Where asynchronous counter is consisting also a group of flip-flops, the same amount of flip-flops which are there in the synchronous counter, the same number of flip-flops are available in the asynchronous counter also, but all the clock pulses are not connected to a single clock pulse. So the first flip-flop clock pulse is depends upon the first system in a clock, and the second clock pulse is depends upon the maybe first flip-flop output, maybe some gate output. So all the clock pulses are not connected in this asynchronous counter with a single clock pulse. Okay, so that we will see in the coming slides. Right. Now coming to that, we will see in this class 2-bit counters. In this class, we will see the 2-bit counters. So for implement, here we have 4 varieties of 2-bit counters. The first one, 2-bit asynchronous upcounter. So the asynchronous counters are also called ripple counters. So if any place, if they said that it is a ripple counter, that is automatically an asynchronous counter. So 2-bit asynchronous up counter, 2-bit asynchronous down counter, 2-bit synchronous up counter, 2-bit synchronous down counter. So these are the different types of counters now we are going to concentrate. Right. So first we will see 2-bit ripple counter. We will see first the concept of 2-bit ripple counter. Before going to that, first we will see which type of flip-flop is used for counting this operation. Okay, so we are using generally a T flip-flop. Generally we are using a T flip-flop or JK flip-flop. So the JK flip-flop, it is nothing but as almost a T flip-flop. When the J and K inputs are shorted together, then it acting as a T flip-flop. So for that reason you can use JK flip-flop and T flip-flop. Right. So here we have JK flip-flop and T flip-flop. These 2 flip-flops we are using for counters. These 2 flip-flops we can use for counters. So for the simplification operation, we are generally using T flip-flop. First see, what is the T flip-flop operation? So first draw the T flip-flop. A T flip-flop is consisting of 1 input and 2 outputs. So the T flip-flop input is nothing but as T and output is Q bar. Okay, right. Here we have only 1 input. That means here we have the maximum possible combinations for the at the input side is 2 only. Why? Because 1 input signal, with using 1 input signal you can give 0 or 1. Right? So you can give either 0, either you can give 1. We can give any one of the value at here. Now see the truth table for the T flip-flop. So T is the input and Q is the output. Okay, if here we have for the T flip-flop, the input is equal to 0 and 1. 2 conditions are available. When you have given the T is equal to 0, the output, the QT plus 1 is equal to QT, and when you have the 1, the output is QT bar. That is, when you have given the 0 when you are giving the 0 input logic for the T flip-flop, it does not work anything. The previous output follows as to the present output. The previous output follows to the present output. But coming to here, when you have given T is equal to 1, the previous output is followed to the present output with a complement operation. Okay, so for example, if you have T input is equal to 0, if the previous output is 1, present output is also 1. If the previous output is 0, present output is also 0. When you have given T is equal to 1 combination, if the previous output is equal to 0, then present output is equal to 1. If the previous output is equal to 1, the present output is equal to 0. So this is the operation we are using for the counters. So most of the times we are using in the T flip-flop operation, T is equal to 1 combination here we are taking. With that combination, we are developing this different types of counters. Okay, right. So for implementing 2-bit counter, I said that previously, for implementing a counter or register, if you want to represent a 2-bit counter, you need 2 flip-flops. If you are developing 4-bit counter, you have to use 4 flip-flops. Like that you have to say. Right. Now we will take 2 T flip-flops. Then we will see the operation. So this is the first T flip-flop and this is the second T flip-flop. Right? So this is the first T flip-flop, this is the second T flip-flop. And we are discussing the concept of 2-bit ripple counter. We are discussing the concept of 2-bit ripple counter. Right? Here I have taken 2 flip-flops. The first 2 flip-flops, this is T1, here I am writing this is T2. T1 and T2. 2 flip-flops I have taken here. And the output is, this is Q1 and this is Q1 bar. And this is Q2 and this is Q2 bar. Okay, 2 flip-flops we have taken and 1 input, 2 outputs. 1 input, 2 output we have mentioned. Right. Next, this one is very important. Here we have a clock signal also for each flip-flop. For each flip-flop we have a clock signal. Okay, we have a clock signal. Very good. Right. So here we have the T input also. For these 2 flip-flops, the first condition is I am giving T is equal to 1 for 2 flip-flops. Here the first condition is I am giving the T input is equal to 1 for these 2 flip-flops. Here T is equal to 1, here T is equal to 1. Okay, T is equal to 1, T is equal to 1. Next, coming to here, I am applying a clock signal here. Here I have applied a clock signal, that is a positive edge clock signal. Positive edge clock signal means what? Here, whenever the clock input is changing from 0 to 1. So see here, the positive edge clock means whenever it is shifting from 0 to 1. That is, when it is observed, the positive edge. When it is observed, the positive edge, then only the flip-flop is going to work. Okay, so whatever the flip-flop, here we have 2 flip-flops. Both the flip-flops are working for the positive edges only. This is very important. So the positive edge is very important. So for the positive edge only the kit is going to work. So you can see here, whenever the signal of the clock input is shifting from 0 to 1, then only it is going to work. Whenever the input of the clock is shifting from 0 to 1, then only this flip-flop is going to work. So here 2 flip-flops are there, 2 clock signals are there. These 2 clock signals, when the logic 0 to logic 1 transition is occurred at these inputs, then only these flip-flops are going to work. Now I have to give one more connection here. So this is very important connection. So see here, the output, the complemented output, the Q bar output I have taken here. The Q bar output I have connected here. The Q bar output I have connected to the clock bus. It is very simple thing. So the second condition is the first flip-flop output, that is Q1 bar, I have connected to the second flip-flop clock signal. Right? I have connected my first flip-flop complemented output to the second flip-flop clock signal. Okay, now see what happened here. Now see here what happened. right? Now see here I am taking T input is equal to 1 1 1 1 1. I have taken all the combinations here. Now I am taking the clock also. Here I am taking the clock also. So give the first clock pulse, second clock pulse, third clock pulse, fourth clock pulse in an order. Next, here we have totally two outputs, Q1, Q2. So see here, I have to write the Q1 output, Q2 output. Okay, this is my condition. Don't write a Q bar value, Q2 bar value. Here you have to write Q1 value and Q2 value. That is, you have to write this output and this output. These values you have to write. Okay, before giving to the here, first see here, before giving to the T is equal to 1, so here actually there is no need of writing T value. Why? Because for all the condition T is equal to 1. So you can neglect this value. There is no need of writing this T value here. So before giving the first clock pulse here, so here I am not giving any clock pulse here. Before giving the clock pulse, the output of the flip-flops are 0 0. That means here this is a Q1, here it is 0 and here it is 0. Okay, now 0 0 are available. Now I am going to give the first clock pulse here. That is, the first positive edge signal is observed here. So the logic is shifting from 0 to 1 here. So whenever I have given the first clock pulse, what is the output? So see here T is equal to 1 and I have given the clock pulse. For the first flip-flop, I have given T is equal to 1. And here we have the clock signal. So whenever the clock signal is observed, if the T input is equal to 1, the previous output is complemented. The previous output is equal to 0. Now the output is equal to 1. Right? So this is the output is equal to 1. And coming to here, when it is shifting from 0 to 1, it is shifting 1 to 0. It is shifting from 1 to 0. Next, right? Next see here. So 1 to 0. Right? Next see here. When it is shifting from 1 to 0, this Q2 flip-flop is not going to work. The Q2 flip-flop is not going to working condition. So it is not in working condition. This is a working in condition. Okay. This is very, very important. So see here. Now write down the Q2, Q1 values here. So here I have taken Q1, Q2. So this is the first Q1 and this is the Q2. So if there is no clock pulse at this flip-flop, then the previous output follows here. So that is, the previous output is 0, the present output is also 0. So you have to write down Q2, Q1 values. Here you have order Q1, Q2 flip-flops. Now you have to write down here Q2, Q1. So the Q2 is equal to 0 and Q1 is equal to 1. Okay, so previously the outputs are 0 0, present the outputs are 1 0 1. Okay, right. Next, go with the second clock pulse. Now I have given again second clock pulse. Now the present values are 1 and here 0. Right? So Q1 value is 1 and Q2 value is 0. Now I have given again the clock pulse. So when I have given the clock pulse, what happened here? The T is equal to 1, T is equal to always 1. So for that reason, whenever you give the clock signal, every time the output is changing here. So the 1 is shifted to 0. When it is, the Q1 is shifting from 1 to 0, the Q1 bar is shifting from 0 to 1. Now it is shifting from 0 to 1. 0 to 1 it is shifting. When it is shifting from 0 to 1, this is as we are giving the clock pulse here. Then this flip-flop is going to inactive situation. When this flip-flop is going to active situation, the D2 input is equal to always 1. So the output is shifting from 0 to 1. Now this output is shifting 0 to 1. Now this output is shifting from 0 to 1. That means the Q2 value is equal to 1 and Q1 value is equal to 0. Now you got the combinations of 1 0. Next, go with the third clock pulse. When you are giving the third clock pulse, so see here, again the operation of the Q1 is again changing from 0 to 1. 0 to 1 it is changing. So that means the Q1 output is changing 0 to 1. Next, see here, when the Q1 is shifting from 0 to 1, Q1 is shifting from 1 to 0. When it is shifting from 1 to 0, this flip-flop is not going to working condition. The previous output follows to the present output. The 1 is followed to the 1 output. Now, the output of this one is equal to 1. So, this is the output behavior of this Q1 and Q2 flip-flops when you are giving the clock pulses. Now, again you have to give the fourth clock pulse. And coming to here, the two outputs of these flip-flops are 1, 1. Here I am writing the first flip-flop, second flip-flop. Both outputs are 1, 1. Okay. So when you have given the clock pulse here, the one is shifting from to 0. So the Q1 is output is shifting 1 to 0. That is over. Next, see here second flip-flop. So when it is shifting from 1 to 0, the Q1 bar complemented output is shifting from 0 to 1. If it is shifting from 1 to 0, it is shifting from 0 to 1. When it is shifting 0 to 1, then this flip-flop is going to working condition, and here the output also is shifting. So that is shifting from 1 to 0. So this is the present condition. Now the both flip-flop outputs is shifting from 1 to 0. Now the output is 0, 0. Now see here, equivalent decimal values for the first combination. Here Q2, Q1, two outputs are available. So 0, 0, write down here 0, decimal value, 0, 1, the decimal value 1, 1, 0, the decimal value 2, 1, 1, the decimal value 3, 0, 0, the decimal value is equal to 0. Right? By using two flip-flops, you can represent the maximum possible combinations 4. So 0, 1, 2, 3. So you can count maximum 4 values only. After completion of 4 values, again you are getting 0. So the flip-flop is going to count from 0 to 3. Here this 2-bit asynchronous or ripple upcounter is counting from 0 to 3. After completion of 3, it is again counting 0 to 3. Okay, so see here once again I am explaining here the concept. So here we have upcounter. Upcounter means the counting is shifting from 0 to 1, 1 to 2 and 2 to 3. After completion of 3, it will become like as a 0. Here we have 2-bit counter. So it is counting 0, 1, 2, 3. That is an ascending order. So upcounter is nothing but as ascending order. 0 to 1, 1 to 2, 2 to 3. After completion of 3, there is no combinations are available by using 2-bit counter. So the next is 0. So by using 2-bit counter, you can count maximum 4 counts only. For example, if you are using 3-bit counter, if you are using 3-bit upcounter, so it is counting from 0 to 7. 2-bit counter counting from 0 to 3. It is counting from 0 to 3. It is counting from 0 to 7. Where 4-bit counter is counting from 0 to 15. Okay. By using 2-bit counter, you can count only 4 values. Okay. By using 3-bit, you can count 8 values. By using 4-bit counter, you can count nearly 0 to 15, 16 values. If you want to count 1024 counts, then you need 10 flip-flops. You need a 10-bit counter you required. So here it is very simple thing. How many counts you want to perform? That first you have to know. So as when you are going to design a counter, first you have to know how many counts you want to count. So based on the value, you have to say this many number of flip-flops I required. Okay. Here by using 2-bit counter, we did 4 counting operations. For example, I am giving 267. I have to perform this many number of counts. If I want to perform 267 counts, then how many flip-flops I required here? How many T flip-flops I required here? So check that combination. Nearly 9 flip-flops you required. So where 2 power 5 is equal to 32, 2 power 6 is equal to 64, 2 power 7 is equal to 128, 2 power 8 is equal to 256. 2 power 8 is equal to 256 and 2 power 9 is equal to 512. Okay, so this value is equal to 267, that is greater than 256. So for that reason, if you want to count 267 values or 267 events, then you need a 9-bit counter. You need a 9-bit counter. That means in that counter diagram, you have to use at least 9 flip-flops. Okay, you have to use 9 flip-flops. Okay, let us see once again the 2-bit counting operation. Here, if you want to do the 2-bit counting operation, here first you take a clock signal and Q1, Q0. Two outputs I have taken. I have previously taken Q1, Q2. Here I have taken Q1, Q0. Both are same only. So the first count, second count, third count, fourth count, fifth count, sixth count. So when I have giving the clock pulse, I am presently considering the outputs are 0, 0. So this one is 0, this one is also 0. So presently the both outputs of the flip-flops I am assuming as it has outputs are 0, 0. So then after 0, 0, actually when you are going to count, so see here, for the second flip-flop, for the second clock pulse, the output is 1. So this value is equal to 0, 1, next 2, next 3, next 0, 1. These are the decimal equivalents of this binary combinations. Like this, the counter has to perform operations. Next, see here, this is a basic 2-bit counter diagram where the T flip-flops are connected each together, but the first flip-flop complemented output is connected to the second flip-flop clock signal. So the first flip-flop clock signal I have connected directly to the clock signal, but the second flip-flop clock signal I am connecting to the first flip-flop complemented output. Then it behaved as an up counter. So this is the up counter truth table, right? And here I am keeping the first condition always t is equal to 1. I have given the first condition for these two inputs of two flip-flops, t is equal to 1. Right? The input I have made 1. And coming to that, the clock signals I have connected. So here for the first flip-flop the clock signal is different. For the second flip-flop the clock signal is different. Okay, so these two clock pulses are connected to two different sources. Right. Okay. Right. Next we will see the 2-bit asynchronous down counter or 2-bit ripple counter. So coming to the 2-bit ripple counter, there is just a small modification from the previous counter to this counter. Anyhow, first see the truth table. So I have taken previously the outputs of the two flip-flops are 0, 0. So when I have given the first clock pulse, the outputs are 1, 1. Then when I have given the second clock pulse, the outputs are 1, 0. When I have given the third clock pulse, the outputs are 0, 1. When I have given the fourth clock pulse, the outputs are 0, 0. Again I got 1, 1. So the counting is repeated here. So here the value of this one is equal to, the value of this one, decimal value of this one is equal to 3, this value is equal to, this value 1, this value 0, this value 3, this value 0. So see here, 3210, again 3210, that is counting going to in the down direction, that is the descending direction. So for that reason, this counter is called down counter. If you want this type of counter, you have to change a small connection. So in the previous concept, we have taken the Q bar signal and we have connected that signal to the clock signal in the up counter. Now I have taken the original output, that is Q output. This Q output I have connected to the second flip-flop clock signal. So for the previous flip-flop and the present flip-flop, the change is only one connection. The connection is in the previous asynchronous up counter, the complemented output I have connected to the second flip-flop clock signal. But in this, I have taken the original output to giving the connection to the second flip-flop clock signal. Right? So now you have to check by giving the clock signals. Okay, so when you are giving the first clock pulse, when you are giving to the first clock signal, so previously I said that both outputs are 0, 0. Okay, so now I have given the first clock signal. When I have given the first clock signal, so see here, that is, here it is positive edge is observed. When it is positive edge is observed, previously I said that this is 0, this is 0. Previously I said that this is 0. This output is 0, this output is 0. Now, when I have given the clock signal, this 0 is shifted to 1 and this 0 is shifted to 1. Okay, now, so see here how these ones are occurred. So, when it is shifting from 0 to 1, when it is shifting from 0 to 1, so see here, this is the behavior for the clock signal. This is the behavior for the clock signal. So, this clock signal value is shifting from 0 to 1. That is, a positive edge is occurred at this clock signal. So, for that reason, this 0 to 1 is occurred. This 0 to 1 is occurred. Previously, both outputs are 0, 0. When I have given the clock signal, when I have given the positive edge here, the output of this flip-flop is shifting from 0 to 1. 0 to 1. When it is shifting from 0 to 1, the clock pulse of the second flip-flop is also activated. Why? Because the positive edge is used for enabling the clock signal. So this flip-flop is also going to working condition. Now, here also the output of the 0 is shifting to the 1. So both outputs are shifting to 1. So that is we have represented here. That is we have represented here. Right. Now again I am giving the next clock signal. When I have given the next clock signal here, right? When I have given the next clock signal here, t is equal to always 1. So the present output is 1. Now this 1 is shifting to 0. Now the 1 is shifting to 0. So when it is shifting 1 to 0, this is not the positive edge. So this flip-flop does not react. Then this 1 is followed to as again 1. This 1 is followed to again as 1. Previous output followed as is 1. Why? Because there is no input change. There is no change in clock. So for that reason, the output previous output only continues here. So the present output is 0 and 1. That 0 1 I have written here like here. For the next combination 1 0 I have represented here. In the same way, you have to check the remaining condition. The next combination is 0 1 and the fifth next combination is 0 0. Then you will get 1 1 value. So here the counting is going to in the downside directions only. So this type of counters are called 2-bit asynchronous down counter or 2-bit triple counter. Right. Next. Now we will start the synchronous counter. Up to now we have seen asynchronous counters are ripple counters. 2-bit asynchronous up counter and 2-bit asynchronous down counter. Now we will see 2-bit synchronous counter, up counter and down counter. So in this slide we will see the up counter. So you have to take the same truth table. There is no change in the truth table. 0 0 0 1 1 0 1 1 0 0 0 1 1 0 1 1. We have the same operation continuously like that. Here we have to change the connections here. Okay, here in the synchronous counters, all the clock flip-flop clock pulses are connected to a single clock pulse. So see here. Here we have the first and second. This is the first flip-flop. This is the second flip-flop. Here the first flip-flop clock signal I connected here. The second flip-flop clock signals also I have connected to a single clock input. Right? That is the two inputs of the clocks. The two inputs of the flip-flops clock signals I have connected here. And here the first condition is connecting to a clock signal to all flip-flops. Next. Here first input of the first flip-flop input is equal to t is equal to 1, and the second t input we are not giving. The second t input is depends upon the first flip-flop output. That is it is depends upon the Q1. It is depends upon the Q1. Now the Q1 has to decide what is the t value. What is the t value? Let us take here one example. Here I am writing t value, and here I am writing Q1 and Q0 values, right? So here clock is there. So here I am giving the first clock signal, and for always the first flip-flop input T1 is equal to 1 1 1 1 1. All these flip-flop outputs are 1 1. Now here I am giving the first clock pulse. When I have given the first clock pulse, there is no change in the first flip-flop operation. So T is equal to always 1. The output is shifting. Previously, the two outputs are I'm assuming as 0, 0. Now I have given the first clock pulse. So the first flip-flop output, that is Q0. Q0 is shifting from 0 to 1. The Q0 is shifting from 0 to 1. Right. So when the output is shifting from 0 to 1, so see here, this is shifting 0 to 1, 0 to 1. That means, so see here, here we have to think we have to remember one information. I have given a same clock signal, a single clock signal for these two flip-flops. Previously, the second flip-flop waits for the first flip-flop output. But these two flip-flops are working at a time. These two flip-flops are working at a time, at the same time. Okay. So when you have given the clock signals, so at that particular time, the input of the first flip-flop is equal to 1 and the second flip-flop input is equal to 0. So when you have given the clock signal, this T is equal to 1 is there. This 1 is shifting from 1 to 0. So when the previous output is equal to 0, the 0 is shifting to 1. So this is over. When coming to the second flip-flop, see here the T input is equal to 0. Why? Because Q0 is equal to 0. So for that reason, when you are giving the second clock signal, at that time T is equal to 0. So if T is equal to 0, previous output is followed to the present output. Okay. So once again, see here, I will explain. Right. So see here, I am giving the clock signal, and here this is a Q1 output, Q0 output. Previously, I have two outputs are 0, 0. So this is the 0 value. Here also we have 0 value. Right. Now I am giving a single clock signal, and both the flip-flops are working at a time. Both the flip-flops are working at a time. So when before giving the clock signal, I have to decide what are the inputs. For this T flip-flop, the input is equal to 1. For this T flip-flop, the output of the flip-flop is equal to T flip-flop input. So here it is 0. That means when I am giving the first clock signal, the first flip-flop T input is equal to 1. The second flip-flop T input is equal to 0. So we know that when after applying the clock signal, if T is equal to 1, the output is shifting. That output is complementing previous output to present output complementing. When the T input is equal to 0, there is no change in the output. So Q0 value is changing here 0 to 1, and Q1 value is not changing. That is, we have to represent with 0 only. Right. So here the present output is 1 and here the present output is 0. Okay. So when you are giving the first clock signal, next coming to the second clock signal. When I have given the second clock signal, check that. Now the present output of Q0 is equal to T, that is T is equal to 1 here. That is the second flip-flop input is equal to 1. We know that for the first flip-flop input always 1. Okay, there is no need of discussing here. Now I have given the second clock signal. So when I have given the second clock signal, here T is equal to 1. So for that reason, the present output is shifting here. Here also T is equal to 1. The present output is going to change here. That is, the 1 is changing to 0. The 0 is changing to 1. Okay. Now I am giving the third clock signal. When I have given the third clock signal, again check what are the inputs. So the present Q0 value is equal to 0. Now here the input is equal to 0 and here the input is always 1. So that is, the Q0 is shifting from 0 to 1 and this 1 is not changing. So the answer is 1. Okay, so after applying the third clock signal, the 0 is shifted to 1, but the 1 is followed as is 1. Okay, why? Because here the T input is equal to 0 at the time of the next clock pulse. So for that reason, the value we got here 0, 0, 0, 1, 1, 0, 1, 1. Okay, these are the behaviors of the 2-bit synchronous upcounter. So when I am giving the clock pulse, first clock pulse, the previous outputs are 0, 0. The previous outputs are 0, 0. So this is the first combination. When I am giving the next clock signal, so check that the Q0 is nothing but as second flip-flop input. So the previous input is here. The input is equal to 0 for the second flip-flop. Now, when you are applying the clock signal, if the input is equal to 0, then there is no change. then there is no change. But when here for the first flip-flop t is equal to 1, for each clock signal, the value of Q0 is changing here. So see here, for all the clock pulses, for each clock pulse, the first flip-flop output, that is Q0, is changing continuously. You can check the behavior continuously, it is changing. Okay, right. Next, whenever the Q output is shifting from 0 to 1. Whenever the Q output is shifting from 0 to 1, then only the behavior you can observe here. That is, here if the value is equal to 1, then only the output is changing. When the Q0 is equal to 1, then only the output is changing. Right? So here Q0 is equal to 1, then you can change the difference of the Q1. When Q0 is equal to 1, you can see the change in the behavior of the asynchronous counter. That is equal to 1 is shifted to 0, 0 is shifted to 1. So you can see the change. You can see the change. Okay, so this is the 2-bit asynchronous up counter. In the same way, we can see the 2-bit down counter. You can see the down counter. Here, the complemented output of the first flip-flop is connected to the second flip-flop T input. That is for down counter. So see here, the down counter. So for the down counter, we have connected the complemented output of the first flip-flop is connected to the second flip-flop T input. So then it acting as a down counter, 0, 0 first count, and next 1, 1, 1, 0, 0, 1, 0, 0, 1, 1. Like that, the count is going to decrement. That is down 3, 2, 1, 0. That is in a descending order. So this is a 2-bit synchronous down counter. Okay, right. Let us see the review of our 2-bit asynchronous and synchronous counters for the up and down counting operations. Let us see. Here we have asynchronous counter. We have seen the 2-bit asynchronous counter with a down counting operation where the complemented output is connected to the next second flip-flop clock pulse, and in the upcounting operation the first flip-flop output is connected to the second flip-flop clock signal. So see here, these two are the asynchronous counters, and the first one is down counting and the second one is up counting. The change you can observe here, the complemented output we are connecting to a clock pulse of the second flip-flop. Here the original output we are connected to the second flip-flop clock signal. Now coming to here, see next synchronous counter. So coming to the synchronous counter, here the common thing is a single clock signal is connected to the all flip-flops. A single clock signal is connected to the all flip-flops. So there is no change in the clock signals. But here we have some of the modifications at the input signal. The first flip-flop input is equal to 1. The first flip-flop original output is connected to the second flip-flop T input. So the first flip-flop output is connected to the second flip-flop input, that is for the T input. So this is for up counting. Next coming to the down counting. So in the synchronous counters, the down counting, the first flip-flop complemented output is connected to the second flip-flop T input. Second flip-flop T input. So this is the down counting. So these two are the asynchronous counters, also called ripple counters. These two are also called ripple counter, and it is the down counting operation. This is the up counting operation, where these two counters are the synchronous counters. In the synchronous counters, a single clock pulse is connected to the all flip-flops. But here the clock pulse in the asynchronous counter for the first flip-flop and second flip-flop are they different. For the first flip-flop, second flip-flop, or the third flip-flop, how many number of flip-flops you are taking in the asynchronous counter? All the flip-flop clock pulses are not same. That is, they have different types of connections and they have different places of sources. But here, a single clock pulse is connected to the all flip-flops for the synchronous counters. It is very, very important. Next, coming to here, the original output is connected to the next flip-flop, then it will do the upcounting operation. The complemented output is connected to the next flip-flop input, that is for T, then it is doing the down counting operation. These are the very, very important observations you have to remember. Okay, when you are doing the activities, when you are doing the counting operations, for example, for 3-bit counting counting or 4-bit counting or 5-bit counting. That is, you are taking 5 bits. With using 5 bits, you can do the countings, 2 power 5 number of countings you can perform. So, for example, you are taking n-bit counter. If you are taking n-bit counter, you can do the 2 power n counts. You can do the 2 power n counts. It is very simple thing. If you are taking a 4-bit counter, you can do 2 power n counting operations. If you are taking a 5-bit counter, you can do 2 power 5 counting operations. That is equal to 32 counting operations. Right? So this is about the review of 2-bit counters. Okay, thank you. Note it down.